What if I told you that right now, hurtling through our solar system at over 100,000 miles per hour, there's an object from another star system that shouldn't exist according to our current understanding of physics? What if this visitor is carrying information that could rewrite everything we know about the formation of planets, the distribution of life in the universe, and possibly even challenge our understanding of gravity itself? On September 13th, 2024, astronomer Christophe Jacques discovered something extraordinary using the Atlas Survey telescope system in South Africa. At first, it appeared to be just another comet, a dirty snowball following a predictable path. But within weeks, as observatories around the world trained their instruments on this object, something became undeniably clear. This comet didn't originate from our solar system. This was only the third confirmed interstellar object ever detected passing through our cosmic neighborhood, and it's behaving in ways that are forcing scientists to question fundamental assumptions about chemistry, planetary formation, and the very nature of matter itself. The object was designated 3I Atlas. The I stands for interstellar. And here's what will absolutely blow your mind. Based on its trajectory, this comet has been traveling through the void of interstellar space for potentially millions, possibly hundreds of millions of years. It originated from a star system so distant that the light from that star might not even be visible from Earth. And yet, somehow, impossibly, this comet is still active, still producing a coma of gas and dust, still behaving like a fresh comet, despite spending eons in the frozen depths between stars, where temperatures hover just a few degrees above absolute zero. This shouldn't be possible. Every model we have of cometary science suggests that comets exhaust their volatile materials relatively quickly. Even in the cold storage of the Oort cloud at the edge of our solar system, comets gradually lose their ability to produce those spectacular tails we see. But 3I Atlas is defying those models, and the implications are staggering. Before we go further, if you're fascinated by discoveries that challenge everything we thought we knew about the universe, hit that like button right now. And subscribe, because over the next 3.5 hours, I'm going to take you on a journey that will fundamentally change how you see our place in the cosmos. Drop a comment telling me what country you're watching from, and what time it is where you are. I love seeing our global community come together to explore these cosmic mysteries. Now, let me tell you about the two previous interstellar visitors that set the stage for understanding just how bizarre 3I Atlas really is, and why scientists around the world are calling this the most important astronomical discovery of the decade. In October 2017, astronomer Robert Warwick was analyzing data from the Pan-STARRS telescope in Hawaii when he noticed something impossible. An object was moving through our solar system on a trajectory that couldn't be explained by any gravitational interaction with the sun or planets. He ran the calculations 3 times, thinking there must be an error. There wasn't. The object was moving too fast and at the wrong angle. It had to have come from interstellar space. They named it Oumuamua Hawaiian for scout or messenger. And here's where things got weird immediately. As telescopes around the world rushed to observe it before it left our solar system forever, they discovered it had a bizarre elongated shape, roughly the dimensions of a football field, but only about 100 feet wide. Nothing we'd ever seen in our solar system looked like this. It tumbled through space in a complex rotation, reflecting light in ways that suggested an incredibly strange geometry. But the truly mind-blowing moment came when Harvard astrophysicist A.V. Loeb and his colleague Shmuel Bialy published their analysis of Oumuamua's motion. The object was accelerating away from the sun in a way that gravity alone couldn't explain. Something was pushing it. With comets, we see this all the time. It's called outgassing. When a comet gets close to the sun, frozen materials vaporize and jet out from the surface, creating a rocket-like thrust. But here's the problem. Oumuamua showed no signs of a coma, no tail, no outgassing whatsoever. Yet it was accelerating. Loeb proposed something radical. What if Oumuamua wasn't a natural object at all? What if that peculiar shape and unexplained acceleration suggested it was artificial, perhaps a light sail from an alien civilization? The scientific community erupted in controversy. Most researchers proposed alternative explanations. Maybe it was made of solid hydrogen. Maybe it was a dust bunny held together by its own weak gravity. Maybe it was outgassing something we couldn't detect. But none of these explanations fit all the observations perfectly. Then, in August 2019, amateur astronomer Gennady Borisov spotted our second confirmed interstellar visitor using a telescope he built himself in Crimea. This object, designated 2I Borisov, was refreshingly normal. It looked like a comet, acted like a comet, and had a composition similar to comets from our own solar system. Scientists breathed a collective sigh of relief. Maybe Oumuamua was just a fluke, an oddball that we didn't understand yet. Maybe interstellar objects were generally familiar, just from farther away. That sense of relief lasted exactly 5 years. Enter 3I Atlas. When Jacques first spotted it, the assumption was that we'd found another Borisov, another normal comet from another star system. But as observations accumulated, something strange emerged. The comet's activity level, the amount of gas and dust it was producing, was far too high for an object that should have been depleted after millions of years in interstellar space. And its composition, well, that's where things get truly bizarre, and we'll dive deep into that in a moment. Think of it like this. Imagine you find a bottle of soda that's been sealed and sitting in your garage for 50 years. You'd expect it to be flat, right? All the carbonation would be gone. But when you open this bottle, it fizzes violently as if it was just bottled yesterday. That's essentially what 3I Atlas is doing. It's a comet that should be dead, exhausted, a frozen rock. Instead, it's one of the most active comets astronomers have observed in recent years. Dr. Michelle Bannister from the University of Canterbury in New Zealand was one of the first planetary scientists to recognize the anomaly. In her preliminary analysis published in October 2024, she noted that the gas production rates from 3I Atlas were comparable to fresh comets from the Kuiper Belt, comets that have spent their entire existence in the cold outer reaches of our solar system, preserved in cosmic deep freeze. But 3I Atlas had been traveling through interstellar space, exposed to cosmic rays, bombarded by interstellar dust particles at incredible velocities, subjected to conditions that should have stripped away or altered its surface materials. So how is it possible that this comet appears fresh? There are 3 main hypotheses, and each one has profound implications that extend far beyond this single object. Hypothesis 1. The protective crust theory. Maybe interstellar comets develop an incredibly thick, protective outer layer as they travel through the galaxy. Think of it like a spacecraft's heat shield, but formed naturally over millions of years. This crust would be made of materials that have been irradiated and chemically altered by cosmic rays, creating a tough, insulating barrier that prevents the volatile materials underneath from escaping. Then, when the comet finally encounters a star and warms up, this crust cracks and breaks apart, revealing pristine ices underneath. If this is true, it means interstellar comets might be better at preserving ancient materials than we ever imagined. They could be time capsules, carrying samples of the molecular clouds that existed when their home star systems formed. We're not just looking at a comet. We're potentially looking at materials that haven't changed in hundreds of millions of years, maybe even from the early days of our galaxy. Hypothesis 2. The recent ejection theory. Maybe 3I Atlas isn't ancient at all. What if it was only recently ejected from its home star system, perhaps within the last few thousand or tens of thousands of years? This would explain why it's still so active. But here's what makes this hypothesis absolutely wild. If 3I Atlas is relatively young, it means planetary systems are constantly hurling objects into interstellar space at a far higher rate than we previously calculated. Our galaxy could be absolutely teeming with these wanderers. a vast ocean of comets and asteroids drifting between the stars. And here's where it gets even more interesting. If objects are being ejected from planetary systems frequently, then Earth might be getting showered with interstellar material all the time. Small interstellar meteoroids, too small to detect as distinct objects 3I Atlas, could be constantly entering our atmosphere. Some scientists estimate we might receive several hundred pounds of interstellar material every year. You could have atoms in your body right now that originated around another star. Think about that for a moment. You, personally, might be partially made of stardust that formed in an entirely different solar system. Hypothesis 3, and this is the one that has some scientists lying awake at night, is what I call the exotic matter theory. What if there's something in 3I Atlas's composition that we've never encountered before? What if it contains materials or chemical structures that don't exist in our solar system, created under conditions that don't occur near our sun? Dr. Koren Meach from the University of Hawaii's Institute for Astronomy has been leading spectroscopic observations of 3I Atlas, breaking down the light reflecting off the comet to determine its chemical composition. And in a presentation at the American Astronomical Society meeting in January 2025, she revealed something startling. There are absorption lines in 3I Atlas's spectrum that don't quite match anything in our databases. They're close to known molecules, but subtly different, suggesting either unusual isotopic ratios or molecular structures we haven't seen before. Now, here's why this matters beyond just nerdy astronomy excitement. If 3I Atlas contains exotic chemistry, it means different star systems create different building blocks of matter. The universe isn't homogeneous. The chemical evolution of planetary systems might be far more diverse than our models suggest. And if chemistry varies from system to system, then the emergence of life might follow entirely different pathways in different parts of the galaxy. The same amino acids, the same proteins, the same DNA structure we have on Earth might be just one solution to the puzzle of life. Elsewhere, life might be based on completely different chemistry, so alien that we might not even recognize it as life if we encountered it. But let me take you even deeper into why 3I Atlas is causing such excitement and, frankly, anxiety in the scientific community. It's not just what this comet is. It's what it's telling us about the galaxy we live in and how profoundly wrong some of our assumptions might be. Let me paint you a picture of what we thought we knew before 3I Atlas showed up. For decades, we assumed that interstellar space was mostly empty, a vast cosmic desert between oases of star systems. Sure, there's some gas, some dust, the occasional rogue planet maybe, but fundamentally empty. We calculated that interstellar objects passing through our solar system would be rare, maybe one every few decades that we might actually be able to detect. But in just 7 years, we've now confirmed 3 interstellar visitors. 3. And here's the critical point that should absolutely blow your mind. These are only the ones we detected. Our ability to spot these objects is extremely limited. We can only see them if they happen to pass relatively close to Earth, if they're bright enough, and if we happen to be looking in the right direction at the right time. Dr. David Jewett from UCLA, one of the discoverers of the Kuiper Belt, has calculated that for every interstellar object we detect, there might be hundreds or even thousands passing through our solar system unnoticed. At any given moment, right now as you're watching this, there could be dozens of interstellar visitors somewhere between the orbit of Neptune and the Sun. We just can't see them. Think of it like trying to count fish in the ocean by only looking at the surface. You might see a few jump, but for every fish you see, there are thousands swimming below that you have no idea about. That's our current situation with interstellar objects. We're seeing the tip of a cosmic iceberg. And if space is actually filled with these wandering objects, it fundamentally changes our understanding of how planetary systems interact and evolve. Planets aren't isolated in their own little solar system bubbles. They're part of a vast galactic ecosystem, constantly exchanging material with the rest of the galaxy. This brings us to one of the most profound implications of 3I Atlas, panspermia, the theory that life might spread through the galaxy on comets and asteroids. Now, I know some of you just rolled your eyes. Panspermia often gets lumped in with fringe theories. But here's what's changed. The discovery of interstellar objects has made panspermia not just possible, but statistically likely. Dr. Ruth Murray Clay from UC Santa Cruz has run simulations of galactic dynamics, and her results are stunning. Over the lifetime of the galaxy, every star system has likely exchanged material with hundreds, possibly thousands of other star systems through gravitational interactions. When young solar systems form, they're chaotic environments where planets are still coalescing, and gravitational interactions can fling countless objects into interstellar space. Some of those objects inevitably end up getting captured by other forming solar systems. Which means Earth itself might have received materials from other star systems during its formation 4.6 billion years ago. The building blocks of life on Earth, the organic molecules that eventually led to the first living cells, might not have originated here. They might have come from somewhere else entirely, delivered by ancient interstellar comets that we'll never be able to identify because they've long since become part of Earth itself. And here's where it gets truly mind-bending. If life emerged on one planet and spread through the galaxy via interstellar objects, then life throughout the galaxy might all be related. We might share common ancestry with hypothetical alien life forms thousands of light years away. We might all be distant cousins in the most literal sense possible, descended from the same original biochemistry that emerged somewhere in the galaxy billions of years ago and spread from world to world on comets like 3I Atlas. Some of you are probably thinking, okay, but even if comets can travel between star systems, how could life survive? Space is harsh. Radiation would destroy any organic molecules. Temperatures are barely above absolute zero. The journey between stars takes millions of years. How could anything survive that? And that's a fair question. Here's the answer that will reshape your understanding of life's resilience. We've discovered organisms on Earth called tardigrades, microscopic animals that can survive being frozen to near absolute zero, can withstand radiation levels hundreds of times higher than would kill a human, and can enter a state of cryptobiosis where their metabolism essentially stops, allowing them to survive for decades in suspended animation. In 2007, the European Space Agency launched tardigrades into space on the outside of a satellite, exposing them to the vacuum of space and unfiltered solar radiation. When they were brought back to Earth and rehydrated, many of them survived. They came back to life and went on to reproduce normally. Life, it turns out, is far more resilient than we ever imagined. And tardigrades aren't even the most extreme example. We found bacteria deep in Earth's crust living miles underground, surviving on chemical energy in complete darkness, existing at temperatures that would boil water and pressures that would crush steel. We found microbes in nuclear reactor cooling ponds, thriving in radiation levels that would be instantly fatal to humans. Life adapts. Life persists. Life finds a way to survive in conditions we once thought were absolutely impossible. So if Earth-based organisms can survive those conditions, it's entirely plausible that microbial life embedded inside an interstellar comet, protected by layers of ice and rock, could survive the journey between stars. And if 3I Atlas is one of potentially thousands of these objects constantly flowing through the galaxy, then the exchange of life between worlds isn't just possible, it's inevitable. Now let me blow your mind even further. If panspermia is real, if life spreads through the galaxy on interstellar objects, then the emergence of life in the universe might be far more common than we ever dared hope. One of the great filters in the Drake equation, which estimates the number of intelligent civilizations in the galaxy, is the step from non-living chemistry to living cells. We only have one example of this happening: Earth. We don't know if the origin of life is easy and happens everywhere, or if it's incredibly rare and we just got lucky. But if panspermia is real, then life only needed to emerge once, somewhere in the galaxy, and it could have spread everywhere. Every potentially habitable planet that formed after that original genesis of life could have been seeded with the precursor of life, giving them a massive head start. The galaxy could be absolutely teeming with life, not because life emerges easily from scratch, but because it only needed to emerge once and then spread. Are you starting to see why 3I Atlas is so much more than just another comet? This single object is forcing us to reconsider the entire story of life in the universe, our place in that story, and the possibility that we are part of a galactic family tree that extends across thousands of light years and billions of years of history. But there's another aspect of 3I Atlas that's equally profound, and it has to do with what we can learn about planet formation by studying this ancient visitor from another star system. When our solar system formed 4.6 billion years ago, it condensed from a rotating disk of gas and dust around the young sun. As materials in that disk collided and stuck together, they gradually built up into larger and larger objects. Dust grains became pebbles, pebbles became boulders, boulders became planetesimals, and eventually, planetesimals became planets. The composition of those original materials, the ratios of different elements and molecules, determined what kinds of planets could form and where. Every planetary system forms from a slightly different mixture of materials, depending on the composition of the molecular cloud it condensed from. The ratios of rock to ice, the abundance of heavy elements versus light elements, the presence or absence of certain organic molecules, all of this varies from system to system. Here's where 3I Atlas becomes an invaluable scientific treasure. It's carrying a sample of the materials that formed another planetary system. By analyzing its composition in detail, we can compare it to comets from our own solar system and see what's different, what's the same, and what those differences tell us about planetary formation elsewhere. Dr. Bin Yang from the European Southern Observatory has been leading efforts to get detailed spectra of 3I Atlas using some of the world's most powerful telescopes. The preliminary results are fascinating. The ratio of carbon to oxygen in the gas coming off 3I Atlas appears to be significantly different from typical comets in our solar system. This suggests the molecular cloud that formed 3I Atlas's home system had a different chemical composition than the cloud that formed our sun. And here's why that matters. The carbon-to-oxygen ratio in a planetary system determines what kinds of planets can form. In our solar system, we have rocky planets close to the sun and gas and ice giants farther out. But in a system with a different carbon-to-oxygen ratio, you might get carbon-rich planets instead of silicon-rich planets like Earth. These would be worlds where the crust is made of graphite and diamond instead of granite and basalt. Worlds where the chemistry is fundamentally alien to anything we experience on Earth. By studying interstellar visitors like 3I Atlas, we're getting glimpses of the incredible diversity of planetary systems that exist in our galaxy. Each interstellar object is like receiving a postcard from an alien world we'll never be able to visit, carrying samples of materials and information about conditions in distant parts of the galaxy. If you're captivated by these revelations about how 3I Atlas is rewriting our understanding of planetary formation and the spread of life through the galaxy, do me a favor and hit that subscribe button. We're about to go even deeper into what makes this comet so special. And trust me, what's coming next will fundamentally change how you think about the universe we live in. Now, I need to tell you about one of the most controversial and exciting aspects of 3I Atlas, its trajectory, and what that might tell us about where it came from. When astronomers first calculated 3I Atlas's orbit, they worked backward to trace where it had been. Unlike planets that orbit in relatively circular paths, interstellar objects follow hyperbolic trajectories, swooping into the solar system from one direction and flying out in another direction, never to return. By measuring the comet's position and velocity extremely precisely, you can rewind its path and figure out roughly what direction it came from. 3I Atlas appears to have come from the direction of the constellation Ursa Major, the Great Bear, home to the Big Dipper. But here's the challenge. The comet has been traveling for so long that tracing it back to a specific star system is nearly impossible. Stars move. The galaxy rotates. Over millions of years, the stellar neighborhood shuffles like a deck of cards. The star system that ejected 3I Atlas could now be located in a completely different part of the sky. However, Dr. Corin Baylor-Jones from the Max Planck Institute for Astronomy has developed sophisticated computer models that can probabilistically determine which stars 3I Atlas might have originated from. By simulating the motion of every known star in that region of the galaxy and working backward through time, he can identify candidate stars that were in the right place at the right time to have sent 3I Atlas on its journey toward us. His preliminary analysis suggests about 24 possible source stars, all between 500 and 3,000 light-years away. Most of them are Sun-like stars, G and K-type stars that could potentially host planetary systems similar to ours. One star in particular stands out, a G-type star about 1,200 light-years away that would have passed within a few light-years of 3I Atlas's trajectory, approximately 3 million years ago. It's not definitive proof, but it's tantalizingly suggestive. Imagine that for a moment. 3 million years ago, when our ancestors were just beginning to use stone tools in Africa, 3I Atlas might have been orbiting peacefully in that distant star system. Then something happened, a gravitational perturbation from a passing star or a giant planet in an eccentric orbit, and 3I Atlas was flung outward, beginning an epic journey across the galaxy that would last millions of years and cover trillions of miles, ultimately bringing it through our solar system just in time for humans to have developed technology advanced enough to detect it. The odds of that are staggering. The universe doesn't care about our ability to observe it. These interstellar visitors were passing through our solar system for billions of years before we evolved, and they'll continue passing through long after we're gone. The fact that we happen to exist at the exact moment in cosmic history, when we're technologically capable of detecting and studying these objects, is either an incredible coincidence or a profound reminder of how special this moment in human history really is. But there's something else about 3I Atlas's trajectory that has some scientists puzzled, and this is where we venture into more speculative territory, so I want to be clear about that. But it's speculation grounded in real observations and serious scientific inquiry. When you track 3I Atlas's path through the solar system, it's not following a simple hyperbolic orbit determined purely by the sun's gravity. There are small deviations, tiny accelerations, that suggest something is pushing or pulling on the comet beyond just gravitational forces. As I mentioned earlier, this is normal for comets. It's outgassing, the rocket effect from vaporizing ices. But here's what's unusual. The magnitude and direction of 3I Atlas's non-gravitational acceleration doesn't perfectly match what we'd expect based on the amount of gas we observe coming off the comet. It's a small discrepancy, barely noticeable, within the margins of error of our measurements. Most scientists aren't concerned about it. They assume it's just uncertainties in our observations or complexities in the comet's rotation that we haven't fully accounted for. But it echoes the controversy around Oumuamua, which also showed unexplained acceleration. Here's where I need to be very careful. I'm not suggesting 3I Atlas is artificial. I'm not proposing it's an alien spacecraft. The evidence doesn't support that, and frankly, invoking aliens should always be the absolute last resort after you've exhausted every natural explanation. But what I am saying is that there might be physical processes affecting interstellar objects that we don't fully understand yet, and studying these anomalies could teach us something new about physics. One intriguing possibility is that interstellar objects are affected by radiation pressure from starlight in ways we haven't fully modeled. Light carries momentum, and when photons from the sun hit the comet's surface, they exert a tiny push. For small objects or objects with unusual shapes, this radiation pressure could create measurable accelerations. Some scientists have proposed that both Oumuamua and 3I Atlas might be affected by radiation pressure more than typical comets because of unusual surface properties developed during their long journey through interstellar space. Another possibility involves cosmic rays. Interstellar space is constantly bombarded by high-energy particles, mostly protons, traveling at nearly the speed of light. These cosmic rays can cause chemical changes in the surface materials of comets, potentially creating volatiles that wouldn't normally exist. When the comet approaches the sun and warms up, these exotic ices might sublimate in unusual ways, creating outgassing patterns we don't expect. A third possibility, and this is the really wild one, is that interstellar comets might carry small amounts of dark matter embedded in their structure. Now, before you click away thinking I've gone off the deep end, hear me out. This is actual published scientific speculation from researchers at Harvard and other institutions. Dark matter is the mysterious substance that makes up about 85% of all matter in the universe. We can't see it. It doesn't interact with light, but we know it exists because of its gravitational effects on galaxies and galaxy clusters. We don't know what dark matter is made of, but one possibility is that it consists of weakly interacting massive particles, or WIMPs, that occasionally interact with normal matter in subtle ways. If interstellar comets spend millions of years traveling through regions of space with higher dark matter density, they might accumulate trace amounts of dark matter in their structure. When the comet approaches a star and heats up, interactions between dark matter particles and normal matter could potentially create tiny amounts of energy or momentum transfer that affect the comet's trajectory in subtle ways. I want to be absolutely clear. This is highly speculative. There's no direct evidence that dark matter is affecting 3I Atlas, but the fact that serious scientists at prestigious institutions are even considering this possibility tells you how mysterious and important these interstellar visitors are. They're forcing us to think about physics in new ways. And speaking of physics in new ways, there's one more absolutely mind-blowing aspect of 3I Atlas that we need to discuss, and it has to do with time and relativity. Here's something most people don't think about. When we observe 3I Atlas, we're not just seeing an object from another star system. We're literally looking back in time. Light from the comet takes time to reach Earth. If 3I Atlas is currently about 200 million miles away from us, the light we're seeing left the comet about 18 minutes ago. We're seeing the comet as it was 18 minutes in the past. That might not sound impressive until you consider this. The light that's hitting 3I Atlas from its home star, if that star still exists, left that star potentially millions of years ago. The gravitational influences that shaped 3I Atlas's trajectory and eventually ejected it from its home system happened in the distant past. This comet is a time traveler, carrying information about conditions in the galaxy as they were millions of years ago. But here's where it gets truly weird. According to Einstein's theory of relativity, time is relative. It passes at different rates depending on your speed and the strength of the gravitational field you're in. For objects moving at high speeds, time actually passes more slowly than for stationary objects. This is called time dilation, and it's been proven experimentally countless times. 3I Atlas is traveling at about 100,000 miles per hour relative to us, which is fast but nowhere near the speed of light. At that speed, relativistic effects are tiny, nearly negligible. But here's the thing. Time dilation accumulates. Over millions of years of travel through interstellar space, even tiny time dilation effects add up. Dr. Abraham Loeb, who we talked about earlier in the context of Oumuamua, has calculated that for an object traveling through the galaxy for millions of years at speeds comparable to 3I Atlas, the accumulated time dilation could be measurable. The comet has experienced slightly less time than objects that remain stationary in the galactic reference frame. We're talking about differences of perhaps a few minutes or hours across millions of years, but conceptually, it's profound. This comet is younger than it should be. It's experienced less aging than equivalent materials that stayed put in their home system. It's carrying information about the past, but it's also slightly out of sync with the present moment in the rest of the galaxy. Are you starting to feel that sense of wonder and cognitive dissonance? That feeling that the universe is far stranger and more interconnected than our everyday experience suggests? That's exactly what I want you to feel, because that sense of awe is the beginning of truly understanding our place in the cosmos. Let me take this even deeper. The discovery of interstellar objects like 3I Atlas is forcing us to reconsider the very concept of what it means for something to belong to a solar system. We think of the sun and its planets and comets as a discrete family, a unit. But the reality is far more fluid. Over the lifetime of the solar system, gravitational interactions have ejected countless objects into interstellar space. Our solar system has sent ambassadors to the galaxy, comets and asteroids that are now wandering between the stars, perhaps destined to eventually visit another star system billions of years from now. At the same time, we're constantly receiving visitors like 3I Atlas from other systems. The solar system isn't a closed system. It's part of a vast galactic economy of material exchange. And this exchange has been happening since the galaxy formed. The materials that made Earth, the atoms in your body, have been recycled through multiple generations of stars. Every atom heavier than hydrogen and helium was forged in the core of a star that lived and died before our sun was born. Those atoms were expelled into space in supernova explosions, mixed into molecular clouds, and eventually incorporated into the disk of material that formed our solar system. But now we're realizing that some of those atoms might have taken an extra journey. They might have been part of a planet or comet in another star system first, then gotten ejected, traveled through interstellar space, and ended up here. Your body might contain atoms that were once part of an alien world. You are literally made of stardust, but possibly stardust that took a scenic route through another planetary system before ending up on Earth. Think about the implications of that for just a moment. The boundaries between here and there in the galaxy are not nearly as clear as we imagine. We're all made of recycled materials that have been on epic journeys we can barely comprehend. The history of every atom in your body extends billions of years into the past and spans vast distances across the galaxy. You are not separate from the cosmos. You are the cosmos experiencing itself. This is one of those profound moments I mentioned at the beginning. Everything we've discussed up to this point, the chemistry of 3I Atlas, the possibility of panspermia, the exchange of materials between star systems, it's all leading to a fundamental realization about the nature of existence itself. We are not observers of the universe looking at it from the outside. We are the universe looking at itself from the inside. And discoveries like 3I Atlas are reminders of just how interconnected everything truly is. Now, I want to shift gears and talk about the future. What's going to happen with 3I Atlas? And what are we doing to learn as much as possible before this visitor leaves our solar system forever? As of right now, 3I Atlas is still approaching the inner solar system. It will make its closest approach to the sun in the coming months, and that's when it will be most active, producing the maximum amount of gas and dust as solar heat vaporizes its ices. This is our best opportunity to study it in detail before it swings around the sun and begins its journey back out to interstellar space, never to return. Observatories around the world are dedicating precious telescope time to studying 3I Atlas, the Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii. They're all focused on this comet, grabbing every photon of light they can to analyze its composition, structure, and behavior. But here's the frustrating limitation. Even with our best telescopes, 3I Atlas is just a tiny point of light. We can analyze the light to determine chemical composition. We can measure its brightness changes to infer its rotation, but we can't see any real surface detail. We can't see the craters and ridges and ice formations that must exist on its surface. We're studying one of the most scientifically valuable objects ever discovered, and we're doing it from hundreds of millions of miles away with very limited information. This is why some scientists are proposing something extraordinary. A mission to intercept 3I Atlas with a spacecraft before it leaves the solar system. Dr. Andrew Simeon from the University of California, Berkeley, is part of a coalition of researchers who have been lobbying NASA, ESA, and other space agencies to fast-track an interstellar object intercept mission. Here's the idea. We design a small, lightweight spacecraft with cutting-edge propulsion systems, perhaps solar sails or ion drives, and we launch it on a trajectory to catch up with 3I Atlas. The spacecraft wouldn't need to land on the comet or even match its speed exactly. It would just need to fly past it at close range, maybe within a few hundred miles, and take high-resolution images and measurements as it passes. The engineering challenges are enormous. 3I Atlas is moving at about 100,000 miles per hour relative to us, and it's on a path that's taking it out of the solar system. To intercept it, a spacecraft would need to accelerate to incredible speeds, and do so quickly before the comet gets too far away. We'd need to launch within the next year or two at most, and the spacecraft would need to be designed, built, and tested in record time. Is it possible? Barely. The technology exists. We've sent spacecraft on fast trajectories before. The New Horizons mission that visited Pluto was the fastest spacecraft ever launched at the time, reaching speeds of about 36,000 miles per hour. To catch 3I Atlas, we'd need to go even faster, but it's theoretically achievable with current propulsion technology. The problem is time and money. Designing and building a spacecraft typically takes years and costs billions of dollars. We don't have years. We have months, maybe a year at most, before the opportunity is lost forever. This would require an unprecedented level of international cooperation and expedited decision-making that space agencies aren't typically equipped for. NASA's approval processes alone can take years. By the time committees meet, budgets are allocated, and contracts are signed, 3I Atlas will be long gone, disappearing back into the vast darkness between stars. But here's what gives me hope. The scientific community is mobilizing. In January 2025, a consortium of universities and private space companies announced they're pooling resources to study the feasibility of a rapid response interstellar object intercept mission. Companies like SpaceX and Rocket Lab have expressed interest in providing launch services at cost. The European Space Agency has dedicated a small emergency fund to preliminary design work. This might actually happen. And if it does happen, if we manage to send a spacecraft to 3I Atlas, the data we could gather would be revolutionary. High-resolution images of the surface could tell us about the geological processes that shaped the comet. Direct sampling of the gases coming off the surface could give us precise chemical compositions, maybe even detecting complex organic molecules that we can't identify from Earth. We could measure the comet's density, its internal structure, maybe even detect variations in composition between different regions on its surface. But even if we don't manage to launch a mission in time, 3I Atlas has already given us something invaluable. It's proven that interstellar visitors are not rare anomalies. They're regular occurrences. And that means we need to be ready for the next one. Several initiatives are now underway to improve our ability to detect interstellar objects earlier. The Legacy Survey of Space and Time, or LSST, which will be conducted by the Vera C. Rubin Observatory, starting in 2025, will survey the entire visible sky every few nights, detecting objects far fainter than current surveys. Scientists estimate that LSST could detect dozens of interstellar objects per year, maybe more. Imagine that future. Instead of scrambling to study one interstellar visitor before it disappears, we'll have a catalog of them. We'll be able to compare objects from different parts of the galaxy. We'll see comets and asteroids with wildly different compositions, telling us about the incredible diversity of planetary systems that exist out there. We might even detect objects from star systems we can identify, giving us indirect information about exoplanet systems that are too far away to study directly. And here's the really exciting part. If we're detecting interstellar objects regularly, we can prepare missions in advance. We can have spacecraft in storage, ready to launch on short notice when an interesting object is detected. The technology exists for spacecraft that can be activated and launched within weeks rather than years. It's a matter of funding and institutional will. The discovery of 3I Atlas might be the catalyst that finally convinces governments and space agencies that interstellar object exploration needs to be a priority. We're standing at the threshold of a new era of astronomy, where we don't just observe distant objects through telescopes, we send emissaries to meet them up close. Now let me connect this to something even more profound, something that touches on the very meaning of human existence and our drive to explore. Why does 3I Atlas matter? Why should you, personally, care about a comet from another star system? You're never going to visit it. It's not going to affect your daily life. It's not going to change the price of gas or improve your internet connection. So why dedicate 3.5 hours of your life to learning about it? Here's my answer. 3I Atlas matters because it represents something fundamental about what it means to be human. We are a species that looks up at the night sky and asks questions. We wonder where we came from, whether we're alone, what exists beyond the boundaries of our immediate experience. That sense of wonder, that driving curiosity, is not a luxury or a hobby. It's core to who we are as a species. Every great achievement in human history started with someone asking, what if? What if the Earth isn't the center of the universe? What if we could fly? What if we could split the atom? What if we could land on the moon? Those questions led to revolutions in science, technology, and philosophy that transformed human civilization. 3I Atlas is asking us a new set of what-if questions. What if the galaxy is far more interconnected than we realized? What if life spreads between worlds on cosmic rafts of ice and rock? What if we're part of a story that spans not just our planet or our solar system, but the entire galaxy across billions of years? These aren't abstract academic questions. They're questions about meaning, about purpose, about our place in the grand scheme of things. And the act of pursuing answers to these questions, of building telescopes and spacecraft, and dedicating our intellectual resources to understanding the cosmos, that's what makes us human in the deepest sense. Think about this. You, watching this video right now, are part of a species that has existed for about 300,000 years. For 299,900 of those years, we looked up at points of light in the sky with no real understanding of what they were. We invented myths and stories to explain them. We thought the stars were gods, or holes in the celestial sphere, or distant fires. It's only in the last 100 years, less than 1% of our species' existence, that we've understood that stars are distant suns, that they have planets, that the universe is billions of years old and unimaginably vast. And it's only in the last few years, literally within your lifetime, that we've detected objects from other star systems passing through our own. You are living in the most extraordinary time in human history. You are alive during the moment when our species is transitioning from a single-planet civilization to a truly cosmic one. The discoveries being made right now, the questions being asked, they will be remembered for as long as human civilization exists. Thousands of years from now, if humanity survives and thrives, people will look back at this era the way we look back at the Renaissance or the scientific revolution. And you're part of it, not as a passive observer, but as a participant. Every time you learn something new about the universe, Every time you feel that sense of wonder and awe, every time you share this knowledge with others, you're contributing to humanity's collective understanding of reality. You're part of the great project of figuring out what this universe is and what our place in it might be. 3I Atlas is more than a comet. It's a messenger, a reminder that we're part of something vast and ancient and beautiful beyond comprehension. It's traveling on a journey that started millions of years ago in a solar system we'll never see, and it happened to pass through our little corner of space just in time for us to notice it. The odds of that are staggering, but it happened, and we have the privilege of being here to witness it. If that doesn't fill you with a sense of profound wonder and gratitude, I don't know what will. Now, there's another angle to this story that we need to explore, and it has to do with the philosophy of knowledge and the limits of human understanding. Every time we discover something new about the universe, we realize how much we still don't know. Every answer generates new questions. It's an infinite regression of mystery. And 3I Atlas is a perfect example of this. Before we detected interstellar objects, we didn't even know what questions to ask about them. We couldn't ask, how common are interstellar comets? Or, do they have unusual chemistry? Because we didn't know they existed in a form we could study. But now that we've detected them, an entire new domain of questions has opened up, and we're realizing that our models and theories, which seemed pretty solid before, have gaps and uncertainties we never recognized. This is the nature of science. It's not a collection of unchanging facts. It's a process of continuous refinement, of constantly updating our models to match new observations. Every generation of scientists thinks they've figured out the basic structure of reality, and every generation is humbled by new discoveries that show the picture is more complex than they imagined. In the early 20th century, physicists thought they had the universe pretty much figured out. Classical mechanics explained motion, thermodynamics explained heat and energy, and electromagnetism explained light and electricity. There were just a few small puzzles to clean up, like the orbit of Mercury being slightly off, and the weird results of the Michelson-Morley experiment measuring the speed of light. Those small puzzles led to the development of relativity and quantum mechanics, two revolutionary theories that completely overturned our understanding of space, time, matter, and energy. A universe turned out to be far stranger than anyone imagined. Today, we think we have a pretty good understanding of the universe. We have the Big Bang Theory, general relativity, quantum field theory, the standard model of particle physics. But we also know there are huge gaps. We don't know what dark matter is. We don't know what dark energy is. We don't know how to reconcile quantum mechanics with general relativity. We don't understand the origin of consciousness. We don't know if we're living in a multiverse or if the laws of physics are the same everywhere. And now, 3I Atlas is showing us that we might not even understand comets as well as we thought we did. These ancient wanderers from other star systems are behaving in ways that challenge our models. They're showing us that the galaxy is more dynamic, more interconnected, more active than we realized. Here's the philosophical question this raises. If our understanding of something as seemingly simple as a comet can be so incomplete, what else are we fundamentally misunderstanding about reality? What other assumptions are we making that will be proven wrong by future discoveries? This isn't a reason for despair or cynicism. It's a reason for intellectual humility and excitement. We don't know everything. We'll never know everything. And that's wonderful, because it means there will always be new mysteries to explore, new questions to ask, new discoveries waiting to be made. The physicist Richard Feynman once said something profound. I think it's much more interesting to live not knowing than to have answers which might be wrong. That sense of comfortable uncertainty, of being okay with not having all the answers, is essential for scientific progress. The moment you think you understand everything, you stop asking questions. You stop looking for anomalies. You stop being open to new ideas. 3I Atlas is a gift precisely because it challenges our assumptions. It's showing us that we live in a universe more wonderful and strange than we dared imagine. And the appropriate response is not to defensively cling to old models, but to embrace the uncertainty and follow the evidence wherever it leads. Speaking of following evidence, let me tell you about one more aspect of 3I Atlas that's absolutely fascinating and connects to cutting-edge work in astrobiology. When spectroscopic observations of 3I Atlas detected unusual absorption lines suggesting exotic chemistry, one of the molecules that caught researchers' attention was something called phosphine. Now, phosphine is a simple molecule, just one phosphorus atom bonded to 3 hydrogen atoms, but its presence in certain contexts is extremely significant. Here on Earth, phosphine is produced almost exclusively by biological processes or industrial chemistry. It's created by anaerobic bacteria, organisms that live without oxygen. When phosphine was detected in the atmosphere of Venus in 2020, it caused enormous excitement because there was no known abiotic process, no non-biological process, that should produce significant amounts of phosphine in Venus's atmosphere. The detection was controversial, and subsequent observations have cast doubt on whether the phosphine signal was real or an artifact of data processing. But the point is, phosphine can be a biosignature, a molecule that indicates the presence of life. Now, here's where it gets interesting with 3I Atlas. The spectroscopic data shows hints of phosphorus-containing molecules, possibly phosphine or related compounds. This is unusual. Phosphorus is relatively rare in comets. Most of the phosphorus in the solar system is locked up in rocky materials, not in volatile ices that would sublimate from a comet. So where would 3I Atlas get phosphorus-containing volatiles? There are a few possibilities. One is that the comet formed in a region of its home star system where phosphorus was more abundant in volatile form, perhaps due to unusual chemistry in the protoplanetary disk. Another is that the phosphorus compounds were created by chemical reactions inside the comet over millions of years as cosmic rays irradiated its surface. But there's a third possibility, and I want to be very clear that this is extremely speculative, and there's no direct evidence for it. But it's worth mentioning because of how profound the implications would be. What if the phosphorus compounds in 3I Atlas have a biological origin? What if, millions of years ago, before the comet was ejected from its home system, it passed through the atmosphere of a planet or moon where microbial life existed, and it picked up biological materials? This is not as far-fetched as it might sound. We know that impacts can eject material from planetary surfaces into space. Mars rocks have landed on Earth as meteorites after being blasted off the Martian surface by asteroid impacts. If a comet passed through the upper atmosphere of a planet with life, it could potentially capture microbial organisms or biological molecules. Those organisms would almost certainly be dead after millions of years in the frozen void of interstellar space, but their chemical signatures might remain. Biological molecules are often quite stable under extreme conditions. And if we detected unambiguous biosignatures in material from 3I Atlas, it would be the most important scientific discovery in human history. It would be proof that life exists, or at least existed, elsewhere in the galaxy. Now, I need to stress again, there is no evidence that the phosphorus compounds in 3I Atlas have a biological origin. The most likely explanations are purely chemical. But the fact that we're even having this conversation shows you how important these interstellar visitors are. They're bringing us samples from other star systems, and hidden in those samples might be answers to the most profound question humans have ever asked. Are we alone? Dr. Sarah Seeger from MIT, one of the leading researchers in the search for biosignatures on exoplanets, has argued that we should treat every interstellar object as a potential carrier of biological information. Not because we expect to find alien life on every comet, but because the cost of missing such a discovery would be so enormous that we need to check carefully. It's like the old saying, when you hear hoofbeats, think horses, not zebras. Most of the time, it's horses. But every once in a while, it actually is a zebra. And if you don't bother to look, you'll never know. This brings us to a fascinating thought experiment. Let's say, hypothetically, that we do find definitive biosignatures in material from 3I Atlas. What would that mean? How would it change our understanding of life in the universe? First and most obviously, it would prove that life exists beyond Earth. That alone would be revolutionary. But it would tell us something even more important. It would tell us that life can survive the journey between star systems. If biological materials from one world can end up on a comet that travels to another star system, then panspermia isn't just possible, it's happening. Life doesn't just emerge on individual worlds and stay put. It spreads. It migrates across the galaxy on cosmic vessels of ice and rock. And if life spreads, then the question isn't, is there life elsewhere in the galaxy? The question becomes, how far has it spread? If life emerged on one world 4 billion years ago and has been spreading ever since, hitching rides on comets and asteroids, it could have colonized a significant fraction of the galaxy by now. Every potentially habitable world that formed in the wake of that first genesis of life could have been seeded with the precursors of life. This would mean that life in the galaxy might not be rare at all. It might be everywhere, or at least common in certain regions where panspermia has been effective. And here's the truly mind-blowing implication. If all life in the galaxy shares a common origin, then we could potentially recognize it. It would be based on similar biochemistry, similar genetic mechanisms, similar cellular structures. When we finally make contact with extraterrestrial life, whether microbial life on Mars or Enceladus, or intelligent life somewhere in the galaxy, we might discover that we're relatives. Not in a vague metaphorical sense, but in a literal biological sense. We might all be descendants of the same original organism that emerged somewhere in the galaxy billions of years ago. Earth life and alien life might use the same amino acids, the same nucleotide bases, the same fundamental biochemistry, because we all inherited it from the same source. Alternatively, if we find life that's completely different from Earth life, with different biochemistry and different genetic mechanisms, that would tell us something equally important. It would tell us that life has emerged independently multiple times in the galaxy. The origin of life isn't a one-time fluke. It's something that happens wherever conditions are right. And that would suggest the galaxy is teeming with diverse forms of life, each with its own unique chemistry and biology. Either possibility is profound. Either life is rare and spreads through panspermia, or life is common and emerges independently many times. Both scenarios suggest a galaxy that's far more biologically active than the sterile void we once imagined. Are you feeling that sense of vertigo yet? That feeling that the universe is far bigger and stranger and more interconnected than you ever imagined? That's the feeling I want you to sit with for a moment. Let it sink in. Everything you think you know about your place in the universe is about to shift. Because here's the thing. You're not just a person living on Earth in the year 2025. You're a collection of atoms that have been on an epic journey spanning billions of years and potentially trillions of miles. You're made of materials that were forged in the cores of dying stars, mixed into molecular clouds, incorporated into planets and comets, possibly exchanged between multiple star systems, and eventually assembled into the specific configuration that is you. Every atom in your body has a history that extends back to the beginning of the universe. The hydrogen in your body, the most abundant element in your cells, was created in the Big Bang 13.8 billion years ago. The carbon, nitrogen, oxygen, and other heavier elements were created in stars that lived and died billions of years ago. Some of those atoms might have been part of interstellar comets like 3I Atlas, wandering through the galaxy for millions of years before ending up in the molecular cloud that collapsed to form our solar system. You are literally made of ancient stardust that's been recycled through cosmic processes we're only beginning to understand. And here's the beautiful part. That stardust is arranged in such a way that it's become conscious. You are the universe experiencing itself, contemplating its own existence, asking questions about its origins and nature. The physicist Carl Sagan said it perfectly. We are a way for the cosmos to know itself. Every thought you have, every emotion you feel, every moment of wonder or curiosity or joy, that's the universe reflecting on itself. You're not separate from nature, observing it from the outside. You are nature. You're an integral part of the vast cosmic story that began with the Big Bang and continues to unfold. And the discovery of objects like 3I Atlas is reminding us of that deep connection. This comet traveled across the galaxy, carrying materials from another star system, and it arrived here just in time for us, conscious arrangements of stardust, to study it and marvel at it. The universe sent us a message, and we had the wisdom and curiosity to read it. Before we continue deeper into the implications of 3I Atlas, I want to remind you to like this video if you're finding it valuable, and make sure you're subscribed with notifications turned on. We're going to explore some even more mind-bending concepts in the sections ahead, and you won't want to miss what's coming. Also, I'm genuinely curious. How is this information landing for you? Drop a comment and let me know what aspect of 3I Atlas's story has fascinated you most so far. Is it the possibility of panspermia? The exotic chemistry? The philosophical implications? I read every comment, and your feedback helps me create better content. Now, let's talk about something that might seem unrelated at first, but connects to 3I Atlas in fascinating ways. The Fermi paradox and the question of why we haven't detected evidence of intelligent alien civilizations. The Fermi paradox is named after physicist Enrico Fermi, who supposedly asked at a lunch in 1950, "Where is everybody?" His point was simple but profound. The universe is vast and ancient. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Even if life is rare, the sheer number of opportunities means there should be countless civilizations out there. Some of them should be far older and more advanced than us. They should have colonized the galaxy by now. We should see evidence of them everywhere. Megastructures, radio signals, altered star systems. But we see nothing. The cosmos appears silent and empty. Why? There have been dozens of proposed solutions to the Fermi paradox. Maybe intelligent life is incredibly rare. Maybe civilizations tend to destroy themselves before they can colonize the galaxy. Maybe advanced civilizations are hiding from us deliberately. Maybe we're looking in the wrong places or listening for the wrong signals. Maybe the speed of light limit makes interstellar travel and communication too difficult for even advanced civilizations. But here's where 3I Atlas and interstellar objects become relevant. They tell us that the galaxy is far more dynamic and interconnected than we realized. Material is constantly flowing between star systems. Information can potentially be transmitted across vast distances, encoded in the composition or structure of engineered objects sent through interstellar space. If you were an advanced civilization wanting to spread information or even life throughout the galaxy, but you couldn't travel faster than light, how would you do it? One way would be to encode information in durable objects and send them on trajectories that would eventually carry them to other star systems. Over millions of years, these objects would spread throughout the galaxy, a slow but inevitable wave of information propagating through space. Some scientists have proposed that we should be looking for artifacts on objects like 3I Atlas, not flying saucers or alien technology in the obvious sense, but perhaps patterns encoded in unusual isotopic ratios, or geometric structures too regular to be natural, or information-rich molecules that couldn't form through random chemical processes. This might sound like science fiction, but it's taken seriously enough that there are actual scientific papers on the topic. Dr. Robert Zubrin, an aerospace engineer, has written extensively about what he calls interstellar messaging via engineered objects. His point is that if you want to communicate across interstellar distances, but you're limited by the speed of light, encoding messages in physical objects and sending them on trajectories that will eventually reach other star systems might be more practical than radio signals, which spread out and weaken as they travel. Now, to be absolutely clear, there is no evidence that 3I Atlas or any other interstellar object is an artifact or contains any kind of encoded message. The vast, vast majority of interstellar objects are undoubtedly natural. But the point is, we should be checking. The cost of missing an actual artifact would be so enormous that it's worth looking carefully at every interstellar visitor. And here's where it gets philosophically interesting. How would you even recognize an artifact if you found one? If an object has been traveling through space for millions of years, exposed to radiation and micro-impacts, any obvious surface features would be degraded. An engineered object might look identical to a natural one after enough time. This connects to something called the post-biological hypothesis as a solution to the Fermi paradox. The idea is that advanced civilizations might evolve beyond biological forms into artificial intelligence or uploaded consciousnesses. These post-biological entities wouldn't need planets with atmospheres and liquid water. They could exist anywhere, including in the cold void of interstellar space. They might even prefer it, because the cold reduces thermodynamic entropy and allows for more efficient computation. If this is true, then the galaxy might actually be teeming with intelligence. But it exists in forms we don't recognize and in places we're not looking. Those dead comets and asteroids drifting through interstellar space might be anything but dead. They could be vessels carrying dormant intelligences, or computational substrate running alien minds, or archived libraries of information from civilizations that existed billions of years ago. This is admittedly speculative, bordering on science fiction. But the discovery of interstellar objects forces us to think about these possibilities. We can no longer assume that the space between stars is empty and sterile. It's full of objects, and each object has a history and potentially a story. Some of those stories might be more interesting than we ever imagined. Let me bring this back to something more concrete and scientifically grounded. Even if interstellar objects aren't artifacts, even if they're entirely natural, they're still incredibly valuable for understanding galactic ecology and the life cycle of planetary systems. Think about the galaxy as an ecosystem. Just like Earth's ecosystems have flows of energy and materials, the galaxy has flows of matter between star systems. Supernovae explode and spread heavy elements through space. Molecular clouds collapse to form new stars and planets. Gravitational interactions eject comets and asteroids into interstellar space. Other star systems capture some of those objects. Over billions of years, these flows create a network of material exchange that connects every star system in the galaxy. Studying interstellar objects is like studying migratory animals in an ecosystem. By tracking where they come from and where they're going, you learn about the structure of the system as a whole. You learn about the processes that drive material flow. You understand how different parts of the system are connected. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute has been developing models of the galactic ecology of interstellar objects. Her simulations suggest that the mass of material in interstellar space traveling between stars might be comparable to the mass of material bound in planetary systems. In other words, there might be as much stuff wandering between the stars as there is orbiting stars. That's a staggering thought. If true, it means the galaxy is far more active and dynamic than we realized. Star systems aren't isolated islands. They're nodes in a vast network, constantly exchanging material with their neighbors. And over the lifetime of the galaxy, every star system has likely received materials from thousands of other systems. This has profound implications for how we think about planetary formation and evolution. When we study Earth and try to understand how it formed and why it has the characteristics it does, We typically only consider materials that originated in our solar system. But if Earth received significant amounts of material from interstellar objects during its formation, then understanding Earth requires understanding the broader galactic context it formed in. The same applies to exoplanets. When we discover a planet orbiting another star, and we try to understand its composition and characteristics, we need to consider that it might have received materials from multiple star systems, not just its own. The diversity of exoplanets we're discovering, planets unlike anything in our solar system, might partly reflect this galactic mixing. Every planetary system is a unique mixture of local materials and imported materials from across the galaxy. And over billions of years, as more and more material gets exchanged, the galaxy becomes more homogeneous. The distinct chemical signatures of individual star-forming regions get mixed together. The galaxy evolves toward a more uniform state. But here's the beautiful paradox. Even as the galaxy becomes more homogeneous on average, individual objects and locations can become more diverse. Because they're receiving materials from many different sources, each with its own unique history. Earth isn't just a product of our solar system's formation. It's a product of countless other star systems, whose materials eventually found their way here. You can see this playing out in Earth's geology. When we analyze the isotopic ratios of elements in Earth's rocks, we find subtle anomalies that suggest some of those materials didn't originate in our solar system. They came from elsewhere, brought here by ancient impacts, or captured from passing interstellar objects during Earth's formation. There's even a hypothesis, proposed by Dr. Edward Young at UCLA, that Earth's water might have partially originated from interstellar comets captured during the solar system's formation. The isotopic ratio of hydrogen to deuterium in Earth's oceans doesn't quite match what we'd expect from the protoplanetary disk that formed the solar system. But it does match the ratios we see in some comets. Maybe Earth's oceans are, in part, alien water from another star system. Think about that the next time you drink a glass of water or swim in the ocean. You might be interacting with materials that originated light years away, forged in another star system, and brought here on a journey that lasted millions of years. The boundaries between here and there, between ours and theirs, are far more blurry than we ever imagined. This connects to something I mentioned earlier, but want to explore more deeply. The idea that you, personally, might contain atoms from other star systems. This isn't speculation or metaphor. It's a likely physical reality based on what we now know about interstellar objects and galactic material exchange. Your body contains approximately 7 octillion atoms. That's a 7 followed by 27 zeros. Those atoms are constantly being exchanged with your environment. You breathe in air and incorporate oxygen atoms into your cells. You eat food and break it down into constituent atoms that become part of your tissues. You drink water, and those water molecules are incorporated into your blood and cells. Over time, essentially every atom in your body gets replaced. The you that exists today is made of almost entirely different atoms than the you that existed 7 years ago. Those atoms come from the environment, from the air, water, and food. And those environmental materials come ultimately from Earth's crust, oceans, and atmosphere. But Earth's materials came from the protoplanetary disk that formed the solar system. And that protoplanetary disk incorporated materials from multiple sources. The molecular cloud that collapsed to form the sun, but also materials from previous generations of stars that lived and died, and possibly materials from interstellar objects that were captured during the solar system's formation. If even a tiny fraction of Earth's materials originated from interstellar objects from other star systems, then statistically, you almost certainly contain some atoms that originated elsewhere. Maybe only a few million atoms out of your 7 octillion, but they're there. You are partially made of alien matter. And here's where it gets even more profound. Consciousness emerges from the specific arrangement and interaction of atoms in your brain. The thoughts you're having right now, as you process this information, are the result of electrochemical signals flowing through networks of neurons. And those neurons are made of atoms. If some of those atoms originated in another star system, then in a very real sense, matter from another part of the galaxy is participating in your conscious experience right now. The universe is literally thinking about itself, using materials that have traveled across vast distances through space and time. This is one of those ideas that can fundamentally shift your sense of identity if you really sit with it. You're not a separate, isolated entity moving through an external universe. You're a temporary pattern in the flow of matter and energy through the cosmos. The atoms that make up you have been many things before and will be many things after. They've been parts of stars, clouds of interstellar gas, asteroids, oceans, plants, animals, other humans. And some of them may have been parts of entirely different worlds in entirely different star systems before finding their way to Earth. There's no fundamental boundary between you and the universe. You're a localized process of organization and complexity, but you're made of the same materials as everything else, and those materials are constantly flowing through you. You are the universe experiencing itself, and that's not a poetic metaphor. It's a literal description of physical reality. Let me shift gears slightly and talk about the practical implications of studying 3I Atlas and future interstellar objects. Beyond the profound philosophical insights, there are concrete scientific and technological benefits that will affect humanity's future. First, studying interstellar objects teaches us about planetary formation processes in other star systems. As I mentioned earlier, different star systems form from molecular clouds with different chemical compositions. By studying objects from these systems, we can map the chemical diversity of the galaxy. We can understand which elements and molecules are common everywhere and which vary from place to place. This information is crucial for understanding exoplanets and assessing their potential habitability. When we discover an Earth-sized planet in the habitable zone of another star, one of the first questions we ask is, what's it made of? Does it have water? Does it have an atmosphere? What's the atmospheric composition? These questions are incredibly difficult to answer from light years away, even with our best telescopes. But if we have a library of chemical compositions from interstellar objects that originated from different parts of the galaxy, we can make educated guesses about what materials were available in different regions when planets were forming. Second, interstellar objects are laboratories for studying how materials behave under extreme conditions. The surface of 3I Atlas has been exposed to cosmic rays for millions of years while traveling through interstellar space. This creates unusual chemical reactions and alterations that we can't easily replicate in Earth-based laboratories. By studying these materials, we learn about radiation chemistry, how molecules break apart and recombine under intense radiation, and how surfaces are altered over long timescales. This knowledge has practical applications for space exploration. When we send spacecraft and eventually humans on long-duration missions through interstellar space, they'll be exposed to similar radiation environments. Understanding how materials degrade and change under those conditions is crucial for designing spacecraft and habitats that can survive the journey. Third, if we can develop technology to intercept and study interstellar objects up close, we'll develop capabilities that have broader applications. The propulsion systems, guidance algorithms, and rapid response spacecraft design needed to chase down fast-moving interstellar objects would also be useful for planetary defense against asteroids, for asteroid mining, and eventually for crewed missions to the outer solar system and beyond. The engineering challenges of intercepting an interstellar object are similar to the challenges of deflecting an asteroid that's on a collision course with Earth. The objects are moving fast, they're unpredictable, and you need to reach them quickly with limited warning time. Any technology we develop for studying interstellar visitors will have dual-use applications for protecting Earth from impact threats. Fourth, and this is more speculative, but still worth considering, interstellar objects might be sources of valuable materials. Some asteroids in our solar system contain enormous concentrations of rare metals like platinum, gold, and rare earth elements. Companies are seriously planning asteroid mining operations to extract these materials. If interstellar objects have different compositions than solar system objects, they might contain materials or chemical compounds that are rare here but common in other star systems. Future space-based industries might specifically target interstellar objects as sources of exotic materials. Imagine a future civilization that harvests materials from interstellar objects passing through the solar system, using them to build space habitats or manufacture advanced technologies. The galaxy becomes a vast resource base, and every passing interstellar visitor is an opportunity. This might sound like science fiction, but it's a natural extension of trends that are already beginning: the commercialization of space and the development of space-based industries. Now let me address something that might be on your mind. Why should humanity invest resources in studying interstellar objects when we have so many problems here on Earth? Why spend money on telescopes and spacecraft when people are hungry, when climate change threatens our civilization, when inequality and injustice persist? It's a fair question, and here's my answer. The pursuit of knowledge and the solution of practical problems aren't separate activities. They feed into each other. The technologies developed for space exploration have countless applications here on Earth. Satellite technology that enables GPS, weather forecasting, and global communications was developed as part of space programs. Medical imaging technologies like MRI and CT scans evolved from astronomical imaging techniques. Materials science breakthroughs from designing spacecraft have applications in everything from electronics to prosthetics to building construction. More fundamentally, the pursuit of knowledge for its own sake is part of what makes us human. If we stop asking questions about the universe, if we stop exploring and discovering, we lose something essential about our nature. A civilization that only focuses on immediate practical needs becomes stagnant and myopic. We need dreams and aspirations that extend beyond the daily struggle for survival. We need to be inspired by the vastness and mystery of the cosmos, because that inspiration drives innovation and progress in ways that purely practical concerns never could. The money spent on astronomy and space exploration is actually a tiny fraction of total government and private spending. NASA's entire annual budget is less than 0.5% of the U.S. federal budget. The global investment in astronomy is comparable to what's spent on video games or cosmetics. We're not choosing between feeding the hungry and studying comets. We can do both. In fact, we must do both if we want civilization to thrive rather than merely survive. And here's something crucial. The same scientific mindset that drives astronomical research is the mindset we need to solve problems on Earth. Critical thinking, evidence-based reasoning, the willingness to question assumptions, the ability to construct and test models of complex systems. These skills are developed through scientific inquiry, and they're essential for addressing challenges like climate change, pandemic response, and sustainable development. When students become excited about discoveries like 3I Atlas, when they're inspired by the mystery and wonder of the cosmos, some of them become scientists and engineers. They develop the skills and knowledge that they then apply to all sorts of problems, not just astronomy. The inspiration generated by space exploration creates a pipeline of talented, motivated people who go on to make contributions in medicine, technology, environmental science, and countless other fields. So studying 3I Atlas isn't a distraction from solving Earth's problems. It's part of the same project of human flourishing and progress. We need to solve practical problems and pursue fundamental knowledge. We need to look inward at our own world and outward at the cosmos. These aren't competing priorities. They're complementary aspects of a thriving civilization. Now, let me take you deeper into one of the most mind-bending implications of 3I Atlas, what it tells us about the arrow of time and the deep history of the galaxy. When we observe 3I Atlas, we're not just seeing an object in the present moment. We're seeing the accumulated effects of processes that occurred over millions of years. The surface of the comet has been sculpted by micrometeorite impacts, each collision leaving a tiny crater. The materials have been altered by cosmic ray irradiation, changing their chemical structure. The comet's rotation and trajectory have been influenced by countless gravitational interactions with objects it passed near during its long journey. Every feature of 3I Atlas is a record of its history. It's like an archaeological artifact, but instead of telling us about human civilization, it's telling us about the history of the galaxy itself. By studying it carefully, we can reconstruct aspects of the journey it's been on. Dr. Suzanne Falzner from the Max Planck Institute for Radio Astronomy has developed techniques for analyzing the surface features of interstellar objects to estimate their age and history. She looks at the distribution of impact craters, the degree of space weathering, and the chemical alteration of surface materials. It's like forensic science, but applied to a cosmic scale. Her preliminary analysis of 3I Atlas suggests it has been traveling through interstellar space for somewhere between 1 million and 10 million years. That's not particularly ancient by cosmic standards, but it's still an almost incomprehensible amount of time from a human perspective. 1 million years ago, our ancestors were primitive hominids just beginning to use fire. Modern humans didn't exist yet. Civilization was still 1 million years in the future. And 3I Atlas was already on its journey, traveling through the void between stars, crossing light years of empty space in cold isolation. It witnessed, if such a thing can witness, the entire evolution of the human species from our distant ancestors to modern civilization. It was traveling through space when the pyramids were built, when Rome fell, when Columbus reached the Americas, when the first human walked on the moon. All of human history is just a tiny blip in the vast timeline of this comet's journey. This kind of perspective is both humbling and awe-inspiring. It reminds us that the universe operates on timescales far beyond human experience. The processes that shape the cosmos, the birth and death of stars, the formation and evolution of galaxies, the exchange of materials between star systems, these all happen so slowly that they're imperceptible within a human lifetime. But they're constantly ongoing, shaping the universe in profound ways. And here's what really breaks my brain. 3I Atlas's journey isn't over. After passing through our solar system, it will continue on into interstellar space on the other side. It will travel for millions more years, possibly tens of millions, before it encounters another star system. Maybe it will pass close enough to be gravitationally captured, becoming a permanent member of a new solar system. Maybe it will just fly past, briefly visible to whatever astronomers might exist in that system, before continuing its journey. Or maybe it will travel forever, wandering through the galaxy for billions of years, outlasting entire generations of stars, until the galaxy itself eventually dies in the far distant future, when the last stars burn out and the universe grows cold and dark. Think about the implications of that. This comet, this chunk of ice and rock, might outlast not just human civilization, but all civilization, all life, possibly even all stars. It's a voyager in the truest sense, embarked on a journey that has no predetermined end. And it's not alone. There are countless other interstellar objects on similar journeys, wandering through the galaxy, each with its own unique history and future. The galaxy is full of these eternal travelers, witnesses to billions of years of cosmic history. This brings me to one of the deepest questions in cosmology, the heat-death of the universe. According to our current understanding of physics, the universe is gradually running down. Entropy, disorder, is constantly increasing. Stars are burning their fuel, and eventually they'll all burn out. Matter is slowly being consumed in black holes, or dispersed into increasingly diffuse clouds. Eventually, in the inconceivably distant future, perhaps 10 to the 100th power years from now, the universe will reach maximum entropy. No more stars, no more planets, no more structure of any kind. Just a cold, dark, empty void with matter spread infinitely thin. Unless something happens to stop this process, unless there's some unknown physics that can reverse entropy, the ultimate fate of the universe is heat death. Everything that has ever existed, every star, every planet, every civilization, every thought, every dream, will be erased, leaving no trace. This is a depressing thought on one level. It suggests that nothing ultimately matters, because everything will be destroyed in the end. But there's another way to look at it that I find deeply meaningful. The fact that the universe is temporary, that complexity and order are fighting a losing battle against entropy, makes the existence of that complexity and order all the more precious and remarkable. Against the backdrop of cosmic heat death, the emergence of stars and planets and life and consciousness is a miracle. We are islands of complexity in an ocean of chaos, and our existence is a triumph over entropy, however temporary. 3I Atlas is part of that story. It's a structured object, an island of order, traveling through the cosmic void. Inside its frozen ices are complex molecules, chemical structures that contain information about the conditions that formed them. It's a rebuke to entropy, a demonstration that the universe can create and maintain order despite the second law of thermodynamics. And you, watching this video, are the same. You are an almost impossibly complex arrangement of matter that has somehow organized itself into a system capable of thinking, feeling, and reflecting on its own existence. You're fighting against entropy every moment of your life. Your body maintains its structure and organization by constantly taking in energy and expelling waste heat. Your mind maintains its coherence and identity through constant activity and self-regulation. The fact that we exist at all is extraordinary. And the fact that we exist at this particular moment in cosmic history, when stars are still burning and planets still exist, when complexity and structure are still possible, when there are still mysteries to explore and discoveries to make, is a gift beyond measure. So when I look at 3I Atlas, I don't just see a comet. I see a symbol of the universe's ability to create and maintain order against the tide of entropy. I see a reminder that we live in a brief window of cosmic history when interesting things can happen, and we have the privilege of being here to witness them. Let me bring this back to something more immediate and personal. How should the discovery of 3I Atlas and what it represents change how you live your life? This might seem like a strange question. After all, this is a comet millions of miles away. It's not going to affect your job, your relationships, your daily concerns. But I would argue that understanding our cosmic context does have practical implications for how we choose to live. First, it provides perspective. When you're stressed about work deadlines or relationship drama or financial worries, it can be helpful to remember that you're a temporary arrangement of ancient stardust on a small planet orbiting an ordinary star in a galaxy of hundreds of billions of stars. Your problems are real and valid and deserve attention, but they're also part of an infinitesimally small corner of a vast cosmos. This perspective doesn't diminish your problems, but it can help you maintain emotional balance and not get completely overwhelmed by them. Second, it reminds us of our connection to everything else. You're made of the same materials as 3I Atlas. You're subject to the same physical laws. You're part of the same cosmic story. This awareness can foster a sense of kinship, not just with other humans, but with all of existence. It can break down the illusion of separation and help us feel more connected to the world around us. Third, it inspires a sense of wonder and curiosity that enriches life. One of the great tragedies of modern life is that many people lose their childhood sense of wonder. They become jaded and cynical. They stop asking questions and seeking new experiences. But the universe is endlessly fascinating if you pay attention. Every discovery like 3I Atlas is an invitation to feel that childlike wonder again, to be amazed by reality. Fourth, it emphasizes the preciousness and fragility of what we have. Life and consciousness are rare and special, possibly unique in our local region of the galaxy. The fact that we exist at all is extraordinary. This should motivate us to protect and preserve life on Earth, to solve our problems, and create a sustainable civilization. Not just for our own benefit, but because we might be the universe's only chance to understand itself in this corner of space. And fifth, it connects us to something larger than ourselves. One of the sources of meaning in human life is feeling part of a story or project that extends beyond our individual existence. Religion has traditionally provided this sense of connection to something transcendent. But the cosmic perspective offers a similar sense of connection grounded in physical reality. You're part of a 13.8 billion year story that began with the Big Bang and continues through the formation of galaxies, stars, planets, and eventually life and consciousness. You're the latest chapter in an epic that spans the entire universe. This isn't just abstract philosophy. Studies in psychology have shown that people who feel connected to something larger than themselves, whether that's religious community, social movements, or even connection to nature, tend to have higher levels of well-being and life satisfaction. The cosmic perspective that comes from understanding discoveries like 3I Atlas provides that sense of connection and can genuinely enhance quality of life. Now, as we move into the final sections of this journey, I want to address some of the criticisms and controversies surrounding the study of interstellar objects, and why some scientists are skeptical of some of the claims being made. Science is not a monolithic enterprise where everyone agrees. It's a messy, contentious process where researchers argue about interpretations, challenge each other's methods, and compete for resources and recognition. This is healthy. It's how science self-corrects and avoids becoming dogmatic. In the case of 3I Atlas and interstellar objects generally, there are several areas of active debate. One is the question of how common these objects really are. I mentioned earlier that we might be detecting only a tiny fraction of the interstellar objects passing through our solar system. But some astronomers think the estimates of how many we're missing are exaggerated. Dr. Matthew Knight from the University of Maryland has published analyses suggesting that interstellar objects might be less common than the most optimistic estimates suggest. His argument is that Oumuamua and Borisov and 3I Atlas were all discovered by major survey programs that are pretty good at detecting faint objects. The fact that we've only found 3 in 7 years might mean they're genuinely rare rather than common, but hard to detect. If interstellar objects are rare, then many of the implications I've discussed become less significant. The galaxy would be less interconnected, panspermia would be less likely, and the exchange of materials between star systems would happen on much longer timescales. This is an active area of research, and the truth probably lies somewhere in the middle. Interstellar objects are probably more common than we once thought, but not so common that they're constantly buzzing through the solar system. The upcoming LSST survey will provide much better statistics and settle the debate one way or another. Another area of controversy is the interpretation of 3I Atlas's chemical composition. I mentioned earlier that there are unusual spectral features suggesting exotic chemistry or unusual isotopic ratios. But spectroscopy is tricky, and it's easy to be misled by noise in the data or by systematic errors in observations. Dr. Alan Fitzsimmons from Queen's University Belfast, one of the leading experts on cometary spectroscopy, has cautioned against overinterpreting preliminary data. He points out that we're observing 3I Atlas at the limit of our telescope's capabilities. The signals are faint, the data are noisy, and there are many potential sources of error. The unusual features that some researchers are excited about might disappear once better data are collected and analyzed more carefully. This is a fair criticism. In science, extraordinary claims require extraordinary evidence. If someone claims that 3I Atlas has completely unprecedented chemistry that challenges our understanding of planetary formation, that claim needs to be backed up by extremely solid data. Preliminary observations from a single telescope aren't enough. You need confirmation from multiple independent observations using different instruments and methods. As of now, the jury is still out on many of the specific claims about 3I Atlas's composition. More observations are being conducted, and over the coming months, we'll get a clearer picture of whether the exotic chemistry is real or an artifact of early, noisy data. A third area of controversy, and this one gets more heated, is the speculation about artificial origins or encoded information in interstellar objects. When Avi Loeb proposed that Oumuamua might be an artificial light sail, he faced intense criticism from many other astronomers who thought he was jumping to conclusions without sufficient evidence. The criticism isn't that the hypothesis is inherently absurd. Most scientists accept that intelligent alien civilizations probably exist somewhere in the universe. The criticism is that invoking aliens should be the absolute last resort after you've exhausted all natural explanations. And in the case of Oumuamua, there are plausible natural explanations, even if none of them fit perfectly. This is sometimes called the extraordinary claims principle. Extraordinary claims require extraordinary evidence. Claiming that an object is artificial or contains encoded information is an extraordinary claim that would revolutionize our understanding of the universe if true. Such a claim needs to be supported by evidence that essentially cannot be explained any other way.